So we started the first day of class talking about the whole purpose of statistics. And just to remind ourselves, remember, the whole point was to make a conclusion about the entire population using much smaller samples. So we said that there was some population we wanted to know about. But we said it was not feasible to get data on every single person in the population. For example, if we wanted to know what percentage of all Americans approve of the president, all Americans would be our population. And then we said that wasn't feasible, so instead we're resorting to a sample. And then we said that statistics was about making this inference about the population using the sample. Now, when we first started talking about this example of trying to find what percentage of all Americans approves of the president, we calculated how long it would take to call every single American, and that ended up being on the order of thousands of years, and we said that was completely infeasible. But nowadays, so when we did that, basically we had to call every single American one by one after the other. So that's serial processing. But some of you might have been thinking, well, instead of calling every American one after the other, nowadays we have computers where we can do parallel processing, where we can just throw out a question, for example, on Twitter, and say, do you approve of the president or not? And within seconds, you have people responding, millions of people responding all at once. And so you don't have to do it one after the other. And so, in that sense, maybe this motivation for statistics isn't, you might think it's not as important, but what's your response to that? So, is it more feasible to put a question out on Twitter and just have millions of people all responding, and now you have your data set? In that sense, do we even need statistics anymore if you can get everybody responding all at once? Yeah.
The issue with social media is the anonymity, as well as it may not be a real person, especially with a lot of bots, like automatically replying and interacting with social media posts. And the people responding may not be telling the truth either, and we won't have any real way to track that back to the person that's responding to the post.
Okay, excellent. Anybody want to add to that? Yeah.
It's also just not a controlled environment that you can rely on.
Yeah, excellent. So our goal is to get accurate information about every person that we're concerned with. The issue of nowadays, where you can just instantly get feedback, is that you don't know whether those responses are truthful or not. But not only that, by using Twitter, for example, are we able to get an answer from every person that we're interested in, which is the country?
No.
No, because not everybody uses Twitter, right? So if we try to, for example, collect our sample from everybody who uses Twitter, we ended up talking about what makes a good sample or an ideal sample. So if we try to answer this question by collecting a sample of Twitter users by throwing a question out on Twitter, do you think that that's a good sample? Remember, a good sample has to be representative of the population. So is this sample of only Twitter users, is that representative of the entire country of who they might vote for? Yeah, no, it's not representative. Why is that?
Because only a subsect of the population actually uses Twitter, and an even smaller subsect actually cares about what they're looking at, and isn't just scrolling through, and will actually participate in the voluntary vote.
Okay, excellent. So it turns out that if you just threw a question on Twitter and then use that to try to answer the question of what percentage of the whole country approves of the president, it turns out that that is not a good sample because it's not representative of the population, because now your sample consists of only Twitter users. And maybe only Twitter users will, it'll be biased in the sense of they'll feel predominantly one way towards the president than the other. So maybe only Twitter users are more technologically savvy, or only Twitter users are younger than people who don't use Twitter and so forth. So they're gonna skew one way versus the other. So because of that, ultimately, we're gonna get some form of a sample, whether it's a large sample or a small sample. Ultimately, we're gonna get some kind of sample. And we need to be able to use statistics to make an accurate conclusion about the whole population using that sample. So the point is that even nowadays, where you can get data very quickly, it doesn't make statistics obsolete. In fact, it makes statistics even more important, because you're gonna have to correctly be able to analyze your sample in order to draw the correct conclusion for your population. Okay, so we said that this was the main framework for the class, is this step of the inference. And then we said that once you collect your sample, and assuming it's a good sample based on the qualities that we talked about, that it's representative, random, and also that the sample size is large enough, once we collect a good sample, we want to analyze just that sample directly. And so in analyzing the sample, we first have to organize the sample. And the sample is going to consist of a whole bunch of numbers. For example, a whole bunch of numbers, or a whole bunch of data points. So for example, in this case, if you want to know what percentage of all Americans approves of the president, our sample is going to contain a whole bunch of yes or no's or maybes from people. So how do you think you can organize a whole bunch of numbers or facts that you have in your sample? So how do we go about organizing all this data?
Graphs.
Yeah, good. So graphs. So in organizing, we'll talk about the graphs that we predominantly use in the class, and connected to that will be charts and tables. So that's organizing the data. But aside from that, if we have a whole bunch of numbers in our sample, we might want to reduce them down to a single number that summarizes something important about our data set. So this will be summarizing. And oftentimes the summarizing will be measurements or numbers. And we'll talk about the types of measurements that we often use to summarize a bunch of numbers. For example, we'll use the mean or the median. There's a type of measurement called the standard deviation, which we'll talk about in excruciating detail later. So these are examples of types of measurements or numbers that we'll use to summarize the numbers existing in our data set. So in today's class, this is what we'll talk about. Given that we have a good sample already, that we talked about how we get a good sample last time, how do we organize and summarize that data set? So and then last time, recall that we also talked about assuming that we then do statistics, and after we do statistics, we communicate our results. And remember, one important aspect of communication that we talked about last time had to do with correlation versus causation. And remember, we also talked about how we can design our study in order to correctly capture either correlation or causation, and then communicate that correctly. One other aspect of communication that I wanna go over, before we get to the main point of today's class, is this issue of communication, we have to be cautious of the source of the study. Especially if we're reading another study. So, this is an example that was in your book, but the example has to do with a company named Kiwi. Have you guys heard of the Kiwi brand? So not the fruit, but the company, the brand. Anybody happen to know what it makes? Okay, so Kiwi happens to make shoe polish. And they actually self-funded and conducted a study where they reported results that said that of all the people who go for job interviews and are denied a job, the number one reason that they're denied a job is because their shoes aren't shiny enough. And so you would expect this coming from a shoe polish company. But this happens lots of times in real life in more subtle ways. So for example, there might be a drug that is supposed to do something like lower cholesterol. And so the company that makes that drug might have a reputable research group at a university conduct that research. But then that research is still funded by that drug company. So people aren't gonna often bite the hand that fed them. So this research group might publish results that are biased towards the drug company. So this happens all the time. So you should, when you're reading studies, you should not only tend to the methodology of the study and see whether it's correlation or causation, but also you should pay attention to the source of the study as well. Any questions? Okay, so now let's talk about analyzing the sample and organizing and summarizing numbers in the sample. So let's first start talking about a concept called a distribution. So let me first motivate this with an example. So let's say that I give you guys a test and I look at all the grades that come back. I might be interested in the grade distribution. So what that means is, let's say that for the sake of simplicity, there's only a handful of students in the class with a handful of grades. So let's say that the grades are let's say 73, 77, 82, 94, 95, 97. So let's say that these are all the grades. So I'm interested in knowing the grade distribution for this class. And so the grade distribution is a relationship between all the possible grades and how often they actually occur in the class. So one way that we can show that relationship is a table of two columns. So the first column is all possible grades. And the second column will be how often they actually occur in the data set. So for the all possible grades, we know that grades can start at 0 and they end at 100. So it's natural to list out all possible grades as increments of 10. So going from 0 to 9, 10 to 19, and so forth. So this is pretty arbitrary, but just based on convention and on the fact that grades and letter grades often go in increments of 10, it's natural to organize the grades this way. So let's say we do this. So sets of 10 from 0 to 100. And let's say in the very last group, we have 11 possible grades from 90 to 100, but all the other groups are 10 possible grades from 80 to 89, for example. So in the second column, we would just go through our data set and list how often each category of grades occurs. So in most of these, it's just going to be 0. Because in our data set, in this particular class, there's 0 instances. But the first non-zero instance is gonna show up where?
70, 79?
Yeah, 70, 79, the 70s. So 70, 79, there's gonna be 2. And then 80 to 89, there's gonna be 1. And then the 90s is gonna be 3. So this is an example of a distribution of this grade variable. So a distribution is nothing more than you're looking at a particular variable, in this case grades, and you're looking at the relationship between all possible values of that variable and how often each value of that variable occurs in the data set. And one way that we can show that distribution or represent that distribution is a table of 2 columns. So here we happen to choose how to represent how often each value of the variable occurs as a raw count. So we just counted in our data set how often it occurs. So that raw count technically is called a frequency. So right now, this would be an example of a frequency distribution. So that's because we chose to represent how often each value occurs as a frequency. But let's say we chose to represent how often the values occurs in our data set in a different way. So instead of just a raw count, an absolute count, how else do you think you can represent how often the values in the data set occurs? So maybe not in an absolute sense, but a relative sense. So for example, how would we express the fact that the 70s occurs twice in our data set, but instead of saying it occurs twice, how would we represent it as a percentage?
33.3?
Yeah, very good. So all you would do is take the fact that it occurs twice in the data set, but twice out of how many numbers in the data set? Out of 6. So this occurs 2 out of 6 times in the data set. So as a percentage, this would occur 33 1/3 times. 33 1/3 percentage of the time. So here we're just choosing to represent how often the values occurs in the data set, but as a percentage. So if you only use the first and the third column then that would represent a relative distribution. If you chose to represent how often the values in your data set occurs as a percentage, this would be a relative distribution. So you only need 2 columns to represent a distribution. The second column has to do with how often each value occurs in the data set. If you chose to represent how often each occurs as a frequency, that would be called a frequency distribution. If you chose to represent how often the values occurs in the data set as a percentage, that would be called a relative distribution. All right, any questions? And then likewise, you could easily convert each of these frequencies into percentages, and how would you do that? So how would you represent the one occurring as a percentage? Yeah, just divide by this constant number 6, which represents the total number of grades total. So this would be 1/6, which is 16.6%. And again, this number 3 representing the frequency would as a percentage be 3/6, which would be 50%. Okay, so for distribution, you only need 2 columns. The first 2 columns would be called the frequency distribution. The first and the third column would be a relative distribution. So this is one way that we can represent a distribution, is a table of 2 columns. How else do you think we could represent a distribution? So distribution is showing all possible values along with how often each one occurs. We can do that with a table of 2 columns, or how else could we do that? Yeah.
And X and Y graph.
Yeah, very good. A graph with 2 axes. So each axis would then represent a column. And so let's look at that. And so on the x-axis here, we'll represent the first column, which is all possible grades. And then we're basically gonna copy every row in the first column to this axis. So one way to do this is to label the groups. So this entire group, the width, would be labeled as 0 through 9, and then this entire width of this group would be labeled as 10 through 19, and so forth. So this is one option. But what if we wanted to label not the groups in their entirety, but we wanted to label just the edges, the boundaries? So if we wanted to label just the boundaries, then because of the way that these groups are currently labeled, this would have to be 9 here, and then now we would have to have a new edge. That is 10. And then that ends at 19, and now we'd have to have a new edge that's 20. This is if we chose to label the edges. And then we'd have to have, this would end at 29, then a new edge that starts at 30, and so on. But if we did this, then this becomes very cluttered, very quickly. But this is just trying to copy what we have in the original table. But any ideas on if we wanted to continue to label just the edges and not the groups themselves, then how could we label this so that it's much less cluttered? How could we label just the boundaries here and not just have these successive boundaries so close together? Yeah.
Just have intervals of 10 and mark in between for the specific numbers.
Okay, so let's try that. So do you mean this? So 0 through 10, 10 through 20, 10 through 30, and so forth? Okay, so that's a good suggestion. Let's try that. So let's say that in our original table, if we had a data point that was 10, for example, it's obvious that it goes in the second group. But if we label our graph this way, then if we have, for example, bars with a certain height, this corresponds to how often each group is represented. So if we have a data point that's 10, based on our graph, just looking at it, we don't know whether that data point of 10 should correspond to the first group or the second group, because it's right on the edge. So that's the issue. So, and that's why before we had to break it up so that we had 0 through 9 and then 10 through 20 and so forth, so that if we had a data point of 10, it's clear that it belongs in the second group. So how do you think we can preserve that clearness while still preserving clarity?
Having more of a curve or a best fit graph.
Okay, so let's say that we wanted to keep it as this bar graph. But how would we label the horizontal axis differently? So what we want to do is we want to preserve our original table here. And the reason why the values of the groups of the table were labeled like this is because we're assuming that we can't have decimal grades, for example. And of course we can, but in this example, let's say we don't. And so we're assuming that there's no data point that can fall outside any of these groups. Because there can't be a 9.5, for example, every value that's labeled here is summarizing every data point that could possibly exist. So there can't be a 9.5, there can't be a 9.7, so that's why these are labeled that way. So knowing that there can't be decimal values, for example, we want a boundary here that's basically, that can represent a value that can never land on this boundary. So one way that we can achieve that is if we take these existing values that represent the highest value of the first group versus the lower value of the second group, we take the average of that. That would be 9 plus 10, which is 19, and divide by 2. That would be 19.5, which is 9.5. So if we use a value like 9.5 on the boundary, then we're assuming that there's no data point that exists that could equal 9.5, so now we don't have that issue of, is this data point, does that fall on the left or the right? So the point is when we're transcribing this into graph form, then, and if we want to label just our boundaries, we're gonna label our boundaries in a way that we're taking the average of the upper and lower bounds from successive groups. So the average of 9 and 10 is 9 plus 10 divided by 2, which is 9.5, and then we're going to do the same thing for successive groups. So the average of between the second and the third group will be 19.5. And the third group will be 29.5, and so on. So this is if we want to label just the edges or the boundaries, and we want to make sure that there's no data point that is equal in value to that boundary that you just labeled. Okay, and then anything greater than 89.5, including 100, will that lands in the last group. So this is just an example of transcribing our original table into graph form. So now what we do is we just look at how often each one occurs, and then we draw a bar graph with the appropriate height. So all of these are going to be 0 until you get to the 70s, 80s, and 90s. So at the 70s, we're going to have a height of 2. At the 80s, we'll have a height of 1. And then 90s will have height of 3. And this will be our same distribution, but represented as a graph instead of as a table of 2 columns. So you notice that this bar graph representing distribution, we actually have a special name for it. This is called a histogram. So a histogram is a bar graph that represents specifically a distribution. Any questions?